Yeah, save it.
Okay.
We should theoretically be live. But
And I'm realizing I have no chats open. I
you
can
don't,
fix that.
do you need a chat?
Not really. I like to have the Weekly Space Hangout crew open
Mm-hmm.
just because they do point out when we're doing something stupid.
Just like a constant mention that we're doing things stupid.
Well, it happens occasionally, and it's good to
Yeah.
know.
It's good when someone else catches mistakes and bugs. No question.
Yes.
Uh, so someone was noting in the chat that this is our old time slot. So back in the day, we used to do episodes of Astronomy Cast on Mondays, and then we shifted it to Fridays so it could be on the same day as the Weekly Space Hangout, and then we moved the Weekly Space Hangout to Wednesdays, and Astronomy Cast stayed on Fridays. So, you know, it's the great cycle.
Yes. Life is what it is. We still bring out the podcasts every Monday.
I don't
So
even know what
that
day the podcast is. It Monday? Okay.
the podcast still comes out on
Okay.
Mondays.
All right. Um, let me say hi to a bunch of people. Hello to Amric Mavillas. Oh, let me try this again. Imeric Mavillas. Let me know if I got that. Arnold Post, Astro B, Ben Appleby, Ben Sugden, Brooke Mulgada, Coalfire, Concerned Rabbit, David Harvey, DKTAZ00, Gareth Wheaton, George Lancaster, Gordon Dewis, Graham W., Guido Bibra, Hug Bearcock, Henrik Bo Anderson, Hugo Burnham, John Suffield, Johnny Zed, Larry Beckham, Leonard Clark, Mr. Tom Harbin, Nancy Graziano, Nichols of the Yard, Peter Quinn, Rinstro, Rick Schwartz, Robert Scott, Herrick, Susie Murph, The Denial, Tom Van Scotter, Tony Raggett, XZXFin120965, and Zapfan. Hey, everybody. Welcome to I guess it is a very special episode of Astronomy Cast at a time. And I guess this is the point, right? We're doing an update on what happened with dark energy, and the only way to really do that is to put ourselves into the time and place that we were when we thought about dark energy last time, which is not actually, I was probably sitting in this exact spot when we did our previous episode about dark energy these many years
I
ago.
was not.
You were not.
No.
I didn't read someone's name. You had to say hi, Peter, in the YouTube chat. That's how I know to say hi to people. Quad Libet, you got to be faster, I guess, is the problem. Hello to Ghost World and Rumpelstiltskin and wait a minute. To want Juju. Are you guys just making up names so it's harder and harder for me? No, these are people's real names. And I want to make sure that I respect and mispronounce them with my hilarious Canadian accent. One quick piece of announcement, which is that I'm going to be doing a live QA with my buddy Isaac Arthur tonight at 5 p.m. So, Isaac, I think, is from your neighborhood. So I think we're just going to talk about his favorite parts of Illinois. I think that's what we're going to do. And his fondness for bridges, maybe? I don't know.
We have pretty good frozen custard here.
There you go. Frozen custard. That's what we're going to talk about. Frozen custard, bridges, and maybe traffic. So it should be fun. Join us.
There isn't much traffic here.
No, well, not in your part.
No.
I don't know exactly where he is. Maybe he's in Iowa. Is that the same place? Illinois and Iowa?
No.
No? Okay.
No.
I don't know.
Very much not.
Yeah, so I don't think I've ever seen Isaac Arthur do a live event before, so I'm sort of amazed and surprised that he was willing to he said yes to me. So we will have a good live chat, and hopefully everyone can no, he's from Ohio. Didn't I say that? Illinois, Iowa, Ohio?
You said no, those are all three very different things.
I don't understand your country at all. There's too many little parts of it. You should just have 12 or 13 the way we do.
We have more people.
That's true. Yeah. But yeah, so if you don't know who Isaac Arthur is, he is a futurist and YouTuber and physicist, and just has thinks about the future in ways that we can scarcely comprehend. So it'll be a party. So join us on my YouTube channel at 5 o'clock. There's an event there. You can click for notification. You'll get reminded. Should be fun. Or just a haunting, existential nightmare look into a dystopian future from which none of us will survive. All right, let's do the show. Pamela, are you ready?
Yes. I'm ready, but someone said Schrodinger's curry in the chat, and I now want curry, and I want to know what the heck Schrodinger's curry is. Is it curry that is neither spicy nor mild?
Until you have a taste of it.
Exactly.
And everyone experiences it differently. That sounds about right.
True.
Yeah.
Okay, we'll go with that. Sorry, I apparently got sidelined by the idea of Schrodinger's curry. Okay, I am now.
Let me know when you're ready to press record.
I'm pressing record.
All right.
Hello,
I've also pressed record.
Chad.
Hello, Chad. Here we go. Astronomy Cast, episode 488, Dark Energy Update. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, is the recovering Dr. Pamela Gay, the Director of Technology and Citizen Science at the Astronomical Society of the Pacific and the Director of CosmoQuest. Hey, Pamela, how you feeling?
I'm doing so much better than last week. For those of you who didn't follow my travails on Twitter, I started out with the world's worst head cold, then developed strep throat, and then kind of wanted to die.
Oh.
So I'm doing better now. My voice is back mostly. I think all of me is at about 95%.
Oh, good. Good. That last 5%, though, we won't need it.
I hope not.
All right. So the updates continue. Last week we talked about dark matter, and this week we continue with its partner, dark energy. Of course, they're not really partners unless you consider mysteriousness to be an attribute. Dark energy, that force that's accelerating the expansion of the universe. What have we learned?
Well, put simply, it's even weirder than we thought.
Oh, good. So we know less. Except the things that we do know are that it's weirder.
Yes.
Nice. And we waited 10 years for this. All right. Well, this will be the shortest episode of Astronomy Cast ever. No, all right. So before we go into the big update, let's give people just the baseline. How do we know that there is a thing called dark energy, and what do we think it is? Maybe.
Well, we don't know what it is. I'm just going to lay that out there. We have no idea what it is. How we know that it is, well, when we look at the cosmic microwave background radiation, we see evidence of a rate of expansion. When we look at baryonic acoustic wave oscillations in the early universe as traced out by the formation of large-scale structure, we see evidence of a given acceleration expansion parameter. When we look at supernovae, measuring how far away galaxies are now to how far away they were at this point in the past, at that point in the past, and compare their measured distances with the rate at which they appear to be moving away from us, we then get a different expansion parameter. And the thought was, if we have a constant rate of expansion over time, then we should see a straight line in terms of distance versus recession rate. If we had a decelerating universe, we would see that plot of distance versus redshift have a slight curve in one direction. If we had a accelerating apart expansion, we would see a different curve. And it would be a nice single parameter curve if everything was constant with time. So back in 1998, we realized, well, yes, the universe is not decelerating with time, which we kind of thought was possible, not accelerating, not expanding at a constant rate, which we'd kind of hoped was what was happening because that makes the math real easy. Rather, we found option C, which is the universe is accelerating itself apart. And we thought it was accelerating itself apart at a constant rate. Um, there appeared to be, looking at all of this, roughly 1 proton of energy per cubic meter of space. And that energy was what was doing this constant pushing. And the mysterious thing has been that no matter how we looked at measuring it, it always appeared that there was this constant amount of energy per cubic meter, and that as the universe has grown in size, each new volume added to the universe had the same exact constant amount of, we're calling it energy.
Right. And so, I mean, up until, say, 1998, the researchers had been doing these really, really detailed observations of the cosmic microwave background and the scale of the universe to try and just get at that ultimate question, right? You know, we want to know, is this universe going to crunch back in on itself? Is it just going to keep on coasting forever? Or is it going to keep on coasting forever? Um, and 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 so that was the search, right? That was the search that the team went, various teams actually went in search of back in the late 90s to look at those supernovae, the distance to those supernovae, to say, okay, how far away is that supernova? When did it happen? That'll tell us how much the universe had expanded back then, and then use that to sort of chart the universe's expansion over time. And this was the crazy discovery, which you're talking about, this idea that there is additional energy that was boosting the expansion of the universe.
And this gets tied together with a whole lot of different parameters that we use to describe the universe. One of them is the mass density of the universe. It turns out that if the universe has a certain significantly higher density, it goes crunch. If it has a significantly lower density, it expands forever. If it has this critical density, which we believe we're at, it, without dark energy, will eventually come to a stop given the fullness of time, which we never actually get to. Now, when you throw in this dark energy component, it means that in addition to having to worry about what is the mass density of the universe, you now have to worry about all this other non-mass-like stuff that is contributing to how the universe behaves over time.
There's an amazing, and I can't find the calculation. Ned Wright, who's sort of famous for looking into this kind of thing, put together this amazing graph of the different ways the universe would have expanded if that mass density of the universe was different. And it's this enormous number, like 30 digits long. I forget the exact number. I was looking for it quickly, but it just goes on and on and on and on. And then you get, after, whatever, in the septillions or something, and then you get to the very end at decimal, and if it's 0.8, then you would have an open universe. And if it was 0.2, then you would have a collapsing universe. And if it was right in the middle, then you would have the flat universe that we have. The fact that it's that close, either way, it could be any other number. It could be 10 times as big, a tenth as big. But the fact is, if it was any number that was any different, we would have a dramatically different universe than the one that we do. But dark energy is like this additional sauce that's been stirred in after the fact that is sort of, again, we don't really know, right? But it seems to have some additional factor that is just sort of continuing on where the Big Bang expansion played out.
Yes. And it's one of these things where, so now we have a name. The name came about in 1998 when this whole discovery was made. There were two different supernovae groups that realized this is a thing. And since then, people have been trying to figure out, okay, so is this thing actually energy? Is it that we don't fully understand gravity and gravity still needs an extra term, long live modified Newtonian dynamics? Uh, is it a matter that maybe there's this scalar field in the background that we often call quiescence that our entire universe is just sort of hung on, and this scalar field is what's contributing what we perceive as dark energy? So there's been a lot of, well, what is going on here? And as part of trying to understand in more and more detail what exactly is going on here, we have cosmologists trying to study the problem from two very different perspectives. One set of groups is trying to measure all of the cosmological parameters based on the early universe. So, what is going on with the cosmic microwave background? What is going on with early structure formation? How do we put together all of the pieces to get from moment zero to, well, the beginnings of the universe we now know? The other team is trying to understand it from looking at the universe today and working backwards. So these are the folks that are trying very carefully to constantly improve our distance measurements to Cepheid variable stars, to then use those Cepheid variable stars to measure distances to galaxies, to then look for supernovae in those galaxies and keep extending the distance ladder of things that we can use standard candles, these objects of known brightness, to measure the distance to. So we're working on trying to converge these two methods. But unfortunately, in the process, here's where we have an update. We have confused ourselves because it appears that you get one value for the expansion if you start today and work backwards, and you get a completely different value if you start at the cosmic microwave background and work forwards.
So is this like another example of, oh, we found stars that are older than the universe?
It is going to be along those lines of new physics is going to be required to figure this out.
Or that the measurement, like, do they overlap in their error bars? Like,
Nope.
they don't. Okay, so both of them
No.
are well precise enough that the answer is
Non-overlapping.
not overlapping.
So from Planck, we have at most a Hubble value of 69. So that's, you take the value they want it to be, which is 67.8, you add the error so that this is like the max allowed by their error value, and it gets you to 69. And it's looking from Wendy Friedman's group, it's looking from Adam Rees's group, that the folks who are working on trying to measure this from distance ladder studies, they're getting around 72. And it doesn't sound like a huge difference, but it's a huge difference.
Right. It's back to that, that number where it's off by a tiny little bit. In this case, that's like a lot. 5%?
Yeah.
Yeah. So it's a big number. Okay.
Yeah.
So that's not helpful.
No.
We should just go backwards and do this show, and we will, things will make a lot more sense than they do today.
Well, so this is where people start just making particles up, which, as we know from past episodes, is one of my absolute most hated things for people to do. So here, one of the things that they've tried making up is something called sterile neutrinos. This is a fourth version of a neutrino from the three that we have experimental evidence for. We have no experimental evidence for there to be sterile neutrinos. People have looked for evidence. There is no evidence of sterile neutrinos. But were sterile neutrinos to exist, they would change the required usage of energy to form particles in the early universe. And by changing how the energy got used to form different kinds of particles, you can change what's allowed for other things to have, and essentially just rebalance the early universe. And this slight rebalancing could explain it. So that's one possible explanation if you like to make up particles.
Right, which we, as you mentioned, you don't like. But well, but I mean that's how this works, Pamela. Come on, someone goes, "Hey, I here's a way. There could be this particle," and then they tell the people at CERN to smash particles together, and hopefully that particle will show up. Or they look in their big neutrino detector mine in Sudbury or Ice Cube down in Antarctica, and they find it. So
Yeah, no, they haven't.
not yet, but come on, be patient. This we've only
So
just gone into it.
so the other thing that can happen, which is quite nice, is it could turn out that there's something that doesn't require creating a particle that's at play. So this is where people start doing things like, well, what if it turns out that dark matter in the early universe actually does kind of sort of occasionally work and play well with others? One of the defining characteristics of dark matter is that it doesn't interact via the electromagnetic force. So this means it doesn't interact with radiation. We can't reflect light off of it. It doesn't give off light. It ignores light. It is not a light-loving particle. But what if in the early universe, when the energy density of light was much greater, when there was in general a lot more radiation flying around because everything was smaller and hotter and more compact, what if then, under those circumstances, dark matter was like, meh, I guess I'll interact a little bit? That slight change in behavior that could have caused dark matter to interact just a little bit differently could also explain this discrepancy.
So dark matter was messing with dark energy early on in the universe.
Maybe.
Maybe. All right. So is that it? Like that's like,
No.
okay. We've got some more updates. All right.
So I mean that's not the only thing that
Or
could
sorry,
explain it.
this is the only difference, right? So this is the new discovery that we've made is that two very accurate measurements give different answers for how much is happening, and you've gone through two possible explanations of what it is. There are more.
There are more
Okay.
indeed. So then we get to the possibility that maybe the density of dark energy isn't as constant with time as we think. So if it turns out there is this itty bitty little tiny parts per bazillion change over time with dark energy, that slight change with time, which would be reflected as a non-constant acceleration. So
Uh-oh.
here on Earth, we have like gravity at sea level is assumed to be 9.8 meters per second squared. It is a constant. You can drop things over and over and over with the same atmospheric conditions, with the exact same distance from the center of the Earth, and you will constantly get 9.8 meters per second squared. Well, what if the value of dark energy was such that the rate of change for the expansion of the universe had its own rate of change?
Yes.
So now we
I don't
have
like where this is going.
now we have the universe is accelerating apart, and that acceleration itself has its own term of some
La
sort.
la la. I'm not listening.
Yeah, the math gets really, really, really ugly. I don't think any of us want to listen to this theory because
Right. But
I don't know who wants to do
But
this.
this is leading to the big rip, right?
Well, it depends on the sign. It depends. I mean, it could be that it's an ever slightly slowing acceleration. It could be it's
Okay.
an
Well, that's not so bad then.
yeah. So
But
so
if it is
different
a
things.
increasing one, we get this scenario in a few billion years where the expansion is so great that it tears apart galaxies, it eventually tears apart solar systems, and eventually tears apart atoms and black holes, and there's nothing left. And we don't get to have
It
those trillions and trillions of years huddled up next to a red dwarf star, you know, becoming spiritually enlightened. We just get torn apart at an atomic scale. See, that's why I didn't like where that was going. But
well,
now I'm a little sort of more balanced about this.
and it all depends on how much of this is happening as well. So we have to worry about the size. which can't be that great because otherwise we would have detected it. Sorry. It varies with the size, and it also varies with the sign. Um, so it all comes down to who is wrong.
Right.
Is it the early universe people? Is it the modern universe people? And then there's always the question of, do we actually know where the Cepheid variable stars are? Because if you screwed up your Cepheids, then everything goes downhill from there.
But you already said that the... Okay, so hold on. So what you're saying is that the measurement isn't necessarily wrong, but your measurement stick might be wrong.
Yes.
Okay.
So this is the problem of using the meter stick that the dog chewed the end off of.
Right. That sounds like a problem you occasionally have to deal with.
It is. It is. This is true. So it's not like a dog is going to chew off the distance to a Cepheid variable star, but it's quite possible that we had some sort of a systematic error. We had some sort of a something. And this is where folks like Adam Rees's research team are working to find new ways to use the Hubble Space Telescope to more accurately measure the distance to Cepheids. This is why the good folks working on the Gaia mission are working to verify with greater and greater accuracy the distance to Cepheid variable stars. We need to confirm where the beginning of our meter stick is, and then work on expanding out to get distances to galaxies, get distances, well, to more distant galaxies.
So then I guess where are we at with a dedicated dark energy satellite or survey or ground-based instrument that is going to be the, I don't know, the Planck of its, to do this job, to really measure dark energy as best as we can from the expansion side as opposed to the beginning side?
Ask me after another congressional election.
Right. After another. Didn't you guys ask for one in the last decadal survey?
We did, and it in fact was the highest ranked thing that we asked for.
Mm-hmm.
But the problem that we're dealing with is Trump has said no more W first. Congress has said, we'll fund you for the rest of the year. And so while W First is continuing to get built, many support projects have been canceled because of Trump's desire to end W First.
Right.
So yeah, there are ongoing cancellations taking place.
So what were some of them? There was the dark energy, the joint dark energy mission. There was the dark energy survey telescope. There's a bunch that are sort of in the works at this point.
And so we have down at Hobby Airplane Telescope the HET-DEX project, which is ground-based. It's undergoing early science. The Dark Energy Probe is still in the process of coming up to speed. W First is at the whim of Congress at the moment. Lots of different teams trying to get out ahead before they get canceled, because Trump has said that he doesn't think that we need to be funding dark energy.
But there are, I mean, it's not just a U.S. thing. I mean, there are, there's the Dark Energy Survey is attached to there's a telescope in Chile. So there is a bunch of ground-based missions, and as you said, there is the Gaia mission that is going to do the best job of determining the positions of stars, and hopefully, it's going to turn up a pile of Cepheid variables as well. And there's even things like, even instruments like, Kepler, unfortunately, we lost it, but things like TESS, which can, it has a whole group of scientists that are going to be using it for other purposes beyond just searching for exoplanets. So there is some sort of ideas in the works on how to get more about this data. Do you think this will come back up again, say in the 2020 decadal survey?
Yes.
Number one priority is what, give us as precise a measurement for dark energy as we have for the cosmic microwave background.
I'm not conceited enough to think that I can say what the number one priority of the US research community is going to be. But I feel confident saying that trying to figure out what dark energy is will be one of the top priorities. Um, so we just need to see where it lands next to astrobiology, the search for exoplanets, and all the other mysterious and weird science that's out there. But dark matter and dark energy continue to torture us by not revealing their secrets.
Which one would you say is better along between dark matter and dark energy? I don't even like saying that in the same sentence because they are two completely different things. Maybe they
Yes.
interacted, but they both need to be renamed.
Yes. Yes. Dark matter is stuff. It's a thing. We
Yeah.
need to, just like we have baryonic particles. We can't quite say that all of dark matter is non-baryonic particles, but we need like some word classification to help us with this one. And dark energy, it's not even a stuff, people.
Right.
It's part of cosmology. It's baked into the structure of the universe.
So then, are there any experiments coming up? Any extensive research projects that you're excited about? Any key measurements that people will be able to make when we come back around in 10 years and have this conversation again? Do you think that we will have made progress? What kind of progress do you think will have been made by the time we do the next update on dark energy?
I'm really hoping that as we build more and bigger telescopes and hopefully someday actually launch the James Webb Space Telescope, we are able to converge our two sets of data where we're able to take measurements of the cosmic microwave background, take measurements of early structure formation and baryonic acoustic oscillations. Take these early measurements and converge on measurements that look at distance versus redshift. It's going to mean making a whole lot higher redshift observations of supernovae, and it's going to be a whole lot of detailed work. But I think this kind of converging of data sets to have overlapping domain is going to be one of the things that really needs to happen. Now, I'm just one person, and that's my personal please make your data overlap kind of wishes. I'm sure there are people who do cosmology day in and day out who have different wishes than mine, and luckily they're the ones who will be determining that part of the decadal survey.
So to wrap this up, man, worst update ever.
Yes, but this is why we science.
Yeah. Dark energy, what is it? I don't know. And it looks like we have two measurements now, and the measurements are both accurate enough to know that they're not wrong, but they're different, which is weird.
Yes.
We'll see in 10 years.
Sounds good.
I love these updates. This is a lot of fun. Thanks, Pamela.
Thank you.
Stop the recording. Save the episode. We both got to go pretty quick. I can take just a couple of questions while I'm saving, and then we'll go from there. And there was a couple of things up there that I saw. Oh, here's the number, by the way. 447-225-917-218-507-401-284-015.8. And that grams per cubic centimeter. And if that was the case, then the universe would accelerate apart, or would expand forever apart. While if it ended in 6.0, so 0.2 more, then the universe would coast to a halt after an infinite amount of time. And if it's 0.2, then it's so dense that after about 14 billion years, its neutral gravity brings it back together and it crunches into a big crunch. That is the difference. It's amazing. What did we say this was?
488.
488? Okay.
Mm-hmm. Peter's like, that's 30 minutes of great time wastage. We're sorry.
Yeah. Do we know what we're going to talk about next week? Do you want to do like an update
No.
on black holes?
Yeah, because we now know about medium-sized
Yeah,
ones.
medium-sized. We know about colliding black holes.
Yeah.
So I think there's some interesting stuff there. There's probably some updates on comets, thanks to Rosetta.
Let's not combine those two into one
No, no,
episode,
no, no, no,
however.
no, no. Separate episodes. Separate episodes.
Let's work our way from more cosmological to less
Well, if you
cosmological.
look at our original episodes, right? Like we
Yeah.
right out of the gate went after all these big
Oh
topics
yeah.
and then sort of shut them down to ourselves from that point on, right? We're like, well, that's it. We did an episode on black holes, so I guess we're done, right? Oh,
So
wait, we
let's
can talk
do
about
it.
supermassive black holes, and we did that,
Yeah.
and then we're done. So that would be interesting to talk about other stuff. Larry Beckham wants to talk about ringularies. Now, is that Larry Beckham's people named Larry who have been collapsed into singularities? In the new Kurzgesagt episode, they talked about how you can make a bomb out of a black hole and how you can harness energy from a black hole. And they said that, in fact, if you have a spinning singularity around that, you got the ergosphere, and they call that a ringularity, right? That is it. That is the ergosphere, is a ringularity. And then a bunch of people were like, "Is that a word? Is that a thing?" I don't think so. I think they just were kidding. I mean, the ergosphere is a thing, but I don't think they call it a ringularity. So, unless you know of that,
No.
no. But every time Kurzgesagt does a new episode, everyone wants... It's funny, everyone wants me to do the exact episode that they just did. People are like, I just saw this episode about black holes, using them as bombs. Can you do an episode? I'm like, they just did it. Why would I do that? They did a great job. They're the best. All right. We should wrap things up. You've got a pile of work. I gotta go pick up a dog.
Deal with
from
life.
the vet. Yeah. So apologies to everybody. Sorry we didn't do a longer episode, but remember to come back around today, 5 o'clock on my channel, and I will be talking live with Isaac Arthur. And like I said, his favorite parts about living in Ohio. That's what we're going to be doing. All right.
And we'll see you on Friday to give you an update on black holes.
That sounds good. All right. We'll see you then. Thanks, Pamela.
Bye-bye.
Thanks, everybody.